In this video, we will demonstrate two families of motion primitives for high-speed flight of fixed-wing robotic aircraft through a dense obstacle-rich environment. This work has been motivated by birds like goshawks, which can fly at incredibly high speeds through dense forests. There are two key challenges in designing motion planning algorithms for such settings. First, the algorithms have to identify collision-free paths and the control inputs required to fly them in a very short span of time. Second, the computation of the control inputs has to duly accommodate the nonlinear dynamics which govern the motion of an airplane. In addition, the motion planner should be equipped with maneuvers which can allow the aircraft to backtrack from dense, impenetrable packets of obstacles. The two families of motion primitives introduced in the paper are continuously parameterized in the space of control inputs. The first family of primitives consists of steady 3D turns between 2 points in space with compatible boundary conditions at the initial point. Using the basic equations of motion, we identify three pseudo-control inputs required to fly this arc: the thrust produced by the aircraft, the angle of attack, and the wind axis roll angle. Dedicated inner loop controllers ensure that the angle of attack and the wind axis roll angle of the aircraft match the prescribed values. In order to accommodate the actuator dynamics as the aircraft transits between two successive primitives, we use a novel time delay-based formulation which allows us to derive algebraic formulae for the control inputs required to fly between a given pair of waypoints. The computation of the control inputs is simple, fast, and easy, and duly accommodates the dynamics of the vehicle. These videos show some flight tests of the first family of primitives. The aircraft was hand-launched and asked to fly between two poles located 1/2 meter on either side of the waypoint.
In these videos, the Vicon motion capture system was used to determine the vehicle's position.
Notwithstanding the altitude, which was difficult to regulate in the short times available to us, the aircraft did precisely what was required of it with a success rate of nearly 100%. In addition to the steady 3D turn, we designed an aggressive turnaround maneuver, or an ATA, to help robotic aircraft backtrack from dense pockets of obstacles. The problem of designing an ATA was posed as an optimal control problem. The numerical solution yielded a three-stage motion primitive. In all three stages, the aircraft was pitched up to the stall angle of attack, while the wind axis roll angle command consisted of a bang-bang profile. The length of the first stage of the primitive turned out to be a parameter which could be optimized for the shape of the turning volume. The ATA primitive was demonstrated in experiments using similar inner loop controllers as the steady turns that you saw earlier in the video. The experimental results matched those expected from the theory, and also served to demonstrate the influence of inner loop controllers on the ATA maneuver. The two primitives described in the video provide simple formulae for computing the control inputs required to fly between waypoints or to backtrack from dense pockets of obstacles. With the ability to backtrack, the primitives can be implemented as part of even off-the-shelf motion planning algorithms. In these simulations, an aircraft is launched into a narrow corridor. It performs an ATA immediately after launch. Thereafter, it flies to the goal. By honing the agility of the airframe, the primitives provide a way for robotic aircraft to achieve high-speed flight through a forest.